We will now discuss how Eugyne Goldstein discovered the existence of protons in atoms. In 1886, the German physicist Eugyne Goldstein observed that if a gas was placed in a cathode ray tube whose inner walls were phosphor-coated and a hole was made on the cathode instead of the anode, a faint glow was observed on the end of the tube next to the cathode and a bright glow on the end of the tube next to the anode. So this figure here depicts the one that is used by Eugyne Goldstein. It is a cathode ray tube, but two changes have been made to it. One, it was filled with a known gas, and two, a hole was made through the center of this cathode here. So Goldstein observed that on the right-hand side here, towards the anode end, a bright glow as usual was produced, but on the other side, behind the cathode, a faint glow was produced. Goldstein used his observation of the faint glow on the anode side of the tube to conclude that it was caused by some type of positive charges. For us to understand Goldstein's observation and his conclusion, we need to understand how a neutral gas particle gets ionized based on our present knowledge of atomic composition. So here we are having a hydrogen atom. And of course, we all know hydrogen has one proton and one electron. So if, let us say, hydrogen was placed inside that cathode ray tube, and it was bombarded with fast-moving electrons, which are in the form of cathode rays, and as these rays move towards the anode, they will encounter some of these hydrogen atoms and collide with them. In so doing, electrons from the hydrogen atoms will be knocked off and positively charged hydrogen ions will be formed. So this one depicts how one hydrogen ion becomes positively charged. A cathode ray, which is a fast-moving electron, collides with an electron from the hydrogen atom that gets knocked off, and it leaves a positively charged hydrogen ion here. A similar thing will happen with another neutral gas particle that is different from hydrogen. Let's suppose that this gas particle had 3 protons. Of course, if it is neutral, it had 3 electrons. Similar thing can happen. A cathode ray can collide with this atom here and knock off an electron, as is shown here. But in this case now, a positively charged gas particle is formed that is different from the one that was produced here. In this case, here you're having 3 protons in the nucleus here, and here you're having 1 proton in this nucleus here. Not only it can become positively charged, more of its electrons can be knocked off. So you have more cathode rays coming, okay, and it encounters more than one of the electrons here. So what happens in this case, both of these electrons here, or 2 of these electrons, can be knocked off, and this will leave us now with an ion that's positively charged, okay, but now it has a charge of 2 positive. Now we're going to transfer our understanding or the knowledge that we have gained here to help us to understand why Eugyne Goldstein made his observation. Let us suppose we have some neutral gas particles here. Okay, see what I've done here? I've deliberately made it into a model that you can see is neutral. I put 1 positive charge here and a negative charge here, right? So each of these gas particles here is neutral. Now these are the cathode rays that are peeling off the cathode here. Because of the high voltage that exists between this positive anode here and this negative cathode here, as the electrons are peeled off, they travel with a substantial velocity, with lots of energy, and therefore whenever they collide with these gas particles here, they have the ability to cause ionization. So what I'm showing you here is this. I'm showing you how gas particles here get ionized. So it produces these electrons here. So you have positive charge remaining here, and you have these electrons here. These electrons that are emitted, along with the rest of cathode rays that are coming, lots of other cathode rays are coming outside that are not affected by the gas particles here. So these electrons and the preponderance of cathode rays that are coming there will move on to the anode side of the tube, and that is going to produce the intense glow there. Now this is the point of importance next. What Goldstein believed was this. Now that these are positively charged particles or gas particles, they will not move towards the anode because the anode being positively charged will repel them. Instead, they move towards the negatively charged cathode, and as they move toward the negatively charged cathode, some of them got stuck onto it. But the momentum of some of them and the space here allowed some of them to pass through there. And that was what caused the light glow on that side of the tube. This other picture here gives a better depiction. Here's the gas-filled cathode ray tube. Cathode rays are coming with considerable amount of energy in that direction. The ionized gas particles, electrons that are produced, along with unaffected cathode rays, will move in that direction, and it causes this phosphorescent screen here to glow. And here you have these positive charges that are created because of the ionization of the gas. They move towards the cathode, and because of the momentum of some of them and the space that's created there, it allows some of these to pass through there, and they collided with the phosphorescent screen at the back here, and that causes faint glow there. All right? So all of what you're spoken about there just now is summarized nicely in this paragraph here. So let's read that. As the cathode rays sped towards the anode, they collided with neutral gas particles in the tube and knocked electrons out of them. The cathode rays, along with the ejected electrons, produced a bright glow on the anode where it ended up. Of course, at the back there, to the back side we're talking about of the tube. The faint glow at the cathode end must have been produced by particles that are positively charged, since they move towards a negatively charged cathode. These positive charges must have been created as electrons were knocked out of the neutral gas particles. As these positive charges move towards the cathode, their momentum must have allowed some of them to escape through the hole in the cathode and impinge on its phosphor-coated walls. And that's the explanation of Goldstein's observation and his conclusion. Few things more. So up to this point, Goldstein is only talking about the presence of positive charges. You have to go a little bit further until we end up with the proton. Now listen to this, I read this. By experimentation outside the tube, Goldstein was able to confirm that the particles that produce a faint glow on the cathode end of the tube were indeed positively charged, or they were positive charges. Subsequently, scientists were able to calculate the charge-to-mass ratios for those positively charged gas particles. All right? Now, talk a little bit about charge-to-mass ratios here. Approximately 20 years later, scientists found that the values of the charge-to-mass ratios depended on the nature of the gas that was placed in the tube, and that these were much smaller than that of the electron, which is extremely due to its smaller mass. Let's unpack that a little bit here, okay? Let us say that scientists placed oxygen inside the cathode ray tube, of course, the positively charged ions there will be due to the oxide ions, right? Let's say oxygen had acquired a charge of 2 positive. In this case, we're saying that 2 electrons probably must have got knocked off, right? So its charge to mass ratio will be equal to 2 positive divided by the mass of the atom, which is 16 AMU. In another experiment, let's suppose that nitrogen was placed in the cathode ray tube and 4 of its electrons got knocked out. So its charge will be 4 positive and its mass will be 14 AMUs. Helium, let's say that it acquired a charge of 3 positive. All right, and is that right? Helium has what? Let's say 2 positive. You got to be 2 positive, okay? It can't be 3. And an AMU of 4. Hydrogen will have only 1 positive. So watch this and listen to this. The only atom, the only element that will produce a charge of 1 positive is hydrogen. And the only element that has an AMU of 1. Now look at the charge to mass ratios. Let us determine some trends here. You can see that as you move in this direction here, because the denominators are getting smaller and smaller, and of course it depends on what that is up there too, right? There's an increase in the charge to mass ratio because of the smaller denominators. But the only one that has the highest charge to mass ratio is hydrogen. Of course, the electron has the greatest charge to mass ratio because of small AMU there, okay? So listen to this now. So we are saying all the other gases are capable of producing multiple positive charges, and even when you work out there, none of them will be as great as hydrogen. After numerous trials, they were able to calculate the charge to mass ratio for the gas particle with the smallest quantity of positive charge and the highest charge to mass ratio, and the gas that produced this value consistently was hydrogen. So they placed all different gases in these things and they found the charge to mass ratios, but on a consistent basis, hydrogen was the one that is found to have the highest charge to mass ratio, the one with the smallest positive charge and the smallest AMU. It was found that this smallest positive charge was equal and opposite to the negative charge on the electron, and it had a mass of 1 AMU, or 1 atomic mass unit, and is now termed the proton. So this is how Eugyne Goldstein, along with the work of other scientists later on, were able to discover the proton. All right, finally, in this video, we do the discovery of the neutrons by James Chawdick. Very easy to understand. All right. In 1932, British physicist James Chawdick discovered that when atoms of beryllium were bombarded with high-speed alpha particles, beams of particles were emitted from the beryllium atoms. Analysis of these particles revealed that they were neither deflected by a magnetic nor electric fields, nor did they discharge charged electroscope. These particles were thus neutral in nature. See? Negative. See, they didn't discharge any electroscope. And there's a classical test for something that's neutral. These newly discovered subatomic particles are now called neutrons. So here it is. Fast-moving or highly energetic alpha particles bombarding the beryllium atoms there, okay? The nuclei, right? And then what they observed? They observed that particles are produced at the back there that had those characteristics, are the same mass as the proton, but no charge, and those are called the neutrons.